What we have been doing up till now deals primarily with motion of physical objects, either in a single direction or in a circular fashion. But what we haven't really been talking about is periodic motion.
I stole that this morning. I'm so sorry.
Okay, thank you.
Sandwich between my
That's
stuff.
okay. What we haven't been talking about is what's called periodic motion. Now, in all fairness, circular motion is a type of periodic motion. Periodic motion just means repetitive motion. So when you have objects moving in a circle, we can think of them as traveling with a particular speed along a path, and then that brings up the concept of motion. Or we can talk about the object just moving around and around and around and around, which brings up the idea of periodic motion. And in fact, if you were to take a look at the motion of this mass on this spring, it's very similar in some ways, other than the fact that it's kind of moving back and forth here, but it's moving up and down. It's very similar in some ways to circular motion, because if I have, and I do have one, but the power doesn't work on it. If I have a turntable, and I set up a turntable at the front of the room here, with a light source over here, and I turn off all the lights in the room, and I take an object like this styrofoam cup and I put it on the turntable, the styrofoam cup will be moving around like this. But when you look on the screen, you're going to see a shadow that's going back and forth. And circular motion is, in fact, periodic motion back and forth, while at the same time, periodic motion in this dimension. So circular motion is periodic motion in two dimensions at the same time. Another example of periodic motion, and this is still periodic motion. Another example of periodic motion, and we've talked about this a couple of times in terms of energy, but here I'm really not interested in energy. And you can't all see the bocce ball here, but you can see the string. Is if I move the pendulum over and I let it go, we have a periodic motion. It repeats. It goes back and forth and back again, back and forth and back again. And this type of periodic motion is sometimes called oscillatory motion. And in this unit, we're looking at oscillatory motion and what are called mechanical waves. I would like to show you something to try to bring this into context. If I take a look at a wave, what we would all agree a wave looks like, that's a wave. Would you agree? And when you look at that, something is moving to the right. Would you agree? But nothing physically is moving to the right. Energy is moving to the right. But if I slow this down and you follow any part of the wave, every part of the wave is simply bobbing up and down. Just like every part of this mass, or just like this mass, is bobbing up and down. So if I can, and I don't have the time or the patience to do this, but if I lined up 100 of these masses on 100 springs from the ceiling, and when this one is at the bottom, but just going up, I let this one go from the bottom. So that they're all going to be oscillating with the same rate, but they're all slightly out of sync. It's like row, row, row your boat, and then the next person comes in. You're a verse off each time. And that's what a wave is. The only problem is, when the stuff that's in the wave is undergoing this periodic motion in different locations, it becomes very difficult to see it, doesn't it? For example, with this one, if I do that and I don't show you the points, your brain is going to say something is moving to the right. But if I want to add a point and another point and another point and another point, then you can start to see what's happening here, which is that each of the pieces of the wave are experiencing this periodic motion. By the way, that is not the only type of wave that we're going to be studying. I don't like that one. I'm going to go here. There's another type of wave, and we'll learn about the two different types later, but this is a different type of wave. And when I get it going, it looks like this. And would you agree there appears to be something moving left to right in the big picture? And I can make that even more apparent by doing that. But if you look very carefully, it's pretty cool actually. When you look very carefully, nothing physically moves from one side to the other. All that's happening is those individual lines are just going back and forth. The difference is this is like an accordion. The things are moving back and forth left to right, and the energy is traveling left to right. Whereas when you take a look at this wave, the stuff that makes up the wave is bouncing up and down, and the energy is moving left to right. So I wanted to show that to you because I want to give you an idea of what exactly it is we're talking about when we say oscillatory motion and mechanical waves. Oscillatory motion is periodic motion. This pendulum is still experiencing periodic motion. This mass on this spring in the center of the room is still experiencing periodic motion. If I put this mass on a different spring, it will experience periodic motion. So all three of these things you're looking at, the two springs are the same idea. They're just two different springs and two different masses. Periodic motion. I'll ask you a question here. If I asked you to estimate the period of this, and we're getting a little bit ahead of ourselves, but I want to know how long it takes to repeat. The best thing to do would be to start a stopwatch, say here, and count off 10 complete oscillations. I know, of course, that most of you don't have your phones with you. So I'm going to grab my phone and do that, and I'm going to count off 10 oscillations. And then we can divide by 10, just like with the flying pig. If you want, you can use your phone and see how close I am to yours. So I got my stopwatch ready to go. I'm going to start it. I'm actually going to start it at the bottom. So I'm going to go start, and then I'll count 1, and we'll do it 10 times. I'm going to start on the next one. Here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What'd you get, Alex?
18.89.
I got 18.96. That's, what about you?
I got 20 seconds.
20 seconds?
It's low.
Anybody else do it?
What?
Let's say 19 seconds. 19 divided by 10 is 1.9 seconds. Question for you. What do you think the period's going to be if I do this instead? That's different, isn't it? What do you think it's going to be? Let's find out. I'm going to start now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the same. I'm just because this lesson is very short, I just want to introduce you to a few basic ideas about simple harmonic motion, and you're going to be doing many labs. What if I take, that's a kilogram of mass on there. What if I take half of a kilogram? Do you think it will be the same? What do you think it will be, more or less? I think it'll be half. Okay. start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not a half. It's like, what was it before? 1.9 seconds, we said? So with a kilogram, boy, and if you're watching this on video, this must be absolutely exciting to watch and listen to. And when we had half a kilogram, it's 1.35 seconds. It's not half. I know what the relationship is, and I'm going to try something here and see how close we got. And I suspect it will be very close. I'm going to take 1.9 divided by 1.35. Man, that's close. Guess what that is? The square root of 2. There's a square root in this relationship somewhere. So wait a minute. What about if I go over, and I hope you're learning something from this. I don't think we have to always stick to the script and go, let's go through the notes. I'm going to go over to this little spring, which has a different spring constant, and let's take some time and find the period for this. This is a kilogram. And we've already established it doesn't matter how far you pull it. Okay. I'm going to start, I'm going to have to be a little more on the ball here. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Different spring. One kilogram, 1.15 seconds when I divide by 10. Let's do some science. What do you think the period is going to be if I use half of a kilogram? Well, look at what happened here. This was divided by the square root of 2. So if we take 1.15 divided by the square root of 2, what do you get? Jay? 0.81. So if I count off 10, I should be 8.1 seconds. Right? And I could cheat, but I'm not going to cheat. I'm going to put the 500 gram mass on the second spring. I'm just putting the 1 kilogram mass back here so that it doesn't spring to the ceiling and I can access it. I mean, bouncy springs are fun, aren't they? I'll get this going first. Go grab my phone. It's really going nuts, isn't it? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.2. That's pretty good. So what we actually got was 0.82 seconds, which that's got to be less than 1%, right? So there's some relationship here, everybody. I hope you understand what we've learned here. There's some relationship between the spring constant and the period. Because when I did this spring with a kilogram, I got a different period than that spring with a kilogram. But there's also a relationship between the period and the mass. But apparently, this doesn't matter. If I do this, and I measure the period, and then I do this, and I measure the period, it's the same. How much you stretch it doesn't change the period. Obviously, I can't stretch it, so the spring ruins. Let's talk about this pendulum. So I'm going to measure the period of this pendulum. And by the way, when we learn about pendulums and springs officially, you're going to be doing lab work based on what we're doing right here. So now I'm going to measure the period of this pendulum. I'm going to start when it gets to the top next time. Start. So this is 1, 2. I could probably just measure ones. 3, 4. I'll go 5. 5. I got 15.46 seconds for this pendulum. The period, we're going to call t the period, is 1.55 seconds. You'll have to take my word for it, but this will be a lab you will do. Changing the mass of the pendulum does not affect the period. What about if we do this? Well, let's make a prediction. I told you over here that the period of this oscillating spring is the same as the period now. So the distance away from the middle doesn't change the period. So if that's the case with a pendulum, this should still be the same period. I'm going to start when it gets to the top. Well, I got to reset. Start. 1, 2, 3, 4, 5. Well, I got 14.91, so 1.50 seconds. It's the same. I have a feeling I actually hit stop just a smidgen early. I can't change the pendulum's period by moving it further out. Is there a way I could change the pendulum's period? I'm telling you the mass won't affect it. You know?
Push it. Add energy.
But then it's just going to be going higher. If I push it harder, then that just means I'm going to drop it from a higher height, that's all. But we've established that it doesn't matter. There's a limitation here we'll talk about later, that it has to be a relatively small angle. Okay? It has to be less than about 30 degrees. Jay?
Extend the length.
Right. Change the length. So if I have, took me a while to dream this up. If I do that, well, I have a problem here. I can't measure this. So you guys are going to have to do it. I'll set it in motion. And we'll do for 5 intervals. And you can start whenever you like. And when you have a time for 5 intervals, let me know. Okay. And you know what? I'm going to pause here because I made a pretty serious mistake here. Pretty much the same. I measured for 5, and I got 15.5 seconds. I divided by 10. I should have divided by 5. Okay, I apologize. I don't know, how many of you caught that? No? But I should have divided by 5. So what did you get? What did you get for about this length? If you divide that number by, what's that number?
13.15.
13.15. So somebody divide 13.15 by 5.
2.63.
It's a smaller period, isn't it? And I mean, I think that's pretty obvious, because if I do this, I think it's pretty obvious it's going back and forth more rapidly, isn't it? And if I don't know if I can do this. Right? But as the length of the pendulum changes, it takes longer. So a very long pendulum takes a very long time. So that's what we're going to be studying. Now let's get to the actual lesson, which, as I said, is a very short lesson. This motion that's periodic is sometimes called simple harmonic motion. And simple harmonic motion is any motion that is repetitive with a fixed time interval. Whatever time that was for one oscillation, it was the same time all the time. Even if I let this thing go, I want to get it going good, and we come back an hour from now and it's still moving just a little bit, that period will be the same. It's why it's called simple harmonic motion. The period stays the same. It's not complicated, it doesn't change. Put your phones away, please. The time it takes for a simple harmonic oscillator to complete one complete cycle of its motion is called the period. Well, I already told you that. Warm up. What are some examples of simple harmonic oscillators that we can think of? Now, clearly there's a pendulum and a spring, but I'm talking about things in our world. And don't be handcuffed to the idea that the period's got to be the exact same all the time. I'm talking about things that do that. Yep.
Those old clocks that have the swinging thing.
Right. Grandfather clock. And by the way, the length of the pendulum determines the time it takes to swing back and forth. And if you've ever, I'll see if I can find a video that shows the inner workings. That is connected to a gear, which is connected to other gears. And every time that thing swings in one direction and back, that gear clicks one place over. And it changes the position of the other gears. What keeps it swinging back and forth, because let's face it, this pendulum is already dying down, right? What keeps it swinging back and forth is there's a spring in there that you put a key in and you wind it up. So every time that pendulum gets to the top and the gear clicks, the spring unwinds a little bit, giving it a little bit more energy. Not enough to change the period. So when you have a grandfather clock with a very long pendulum, it's taking longer to swing back and forth. They don't all swing back and forth at 1 second. The only way you can get a pendulum that swings back and forth at 1 second on Earth is to have a very specific length. I can tell you what the length is. It's about 25 centimeters. There's a formula I'm using here that you will learn, but if I make this pendulum 25 centimeters long, from the pivot point to the center of the pendulum bob, that's what the sphere is called, it will swing back and forth once per second. Any others? So, what's the typical period here? It depends on the size of the clock. But again, even if the period is 2 seconds, that doesn't mean you can't tell time by the clock. It's connected to gears that makes the hand on the clock face move the way it should move for time. Other examples? What about some natural examples, not manufactured? Huh?
Would a bungee jump cord be one?
Bungee jumping? Sure. Now, when we say bungee jumping, not the part where you're falling, but the part where it extends and then for a little while you bounce up and down. The only thing that makes it not really ideal is when you bungee jump, probably what happens is when you get to the bottom, you go up so high that the cord unravels kind of thing. The cord doesn't stay stretched. But yeah, bungee jumping would be good. I don't know what the period of oscillation on one of those would be, but it would probably be 5 seconds, 4 seconds. We're just estimating here. What about animals? Are there any animals that have periodic motion? Sure, the wings of a bee or the wings of a hummingbird. Bee is typically the example that we use. bee wing flapping. We don't normally maybe think of the word flapping because flapping seems to imply you can see these wings kind of pushing the air, but a bee's wings are flapping. They're just flapping very, very quickly. I don't know what it is. There might be an example in this lesson that talks about that, but it could be 100 times per second, which means the period would be very small, maybe 100th of a second. Put your phone away, please. Anyway, you can come up with a few other examples. I've already talked about these two main types of simple harmonic motion, the mass swinging on the end of a pendulum and a mass oscillating on the end of a spring. And it could be vertical or horizontal. The problem with horizontal oscillations is you have to put the mass on something and there's going to be friction, so it won't oscillate very often. The problem with this is that not only is there a force on the mass because the spring is acting on it, there's a force of gravity on the mass. So it's complicated to analyze. We have to go through some definitions. Equilibrium position. The equilibrium position of any oscillator, any wave, is the state of affairs when there's no energy in it. So if I say, where is the equilibrium position of this mass on this spring? It's right there. If I use the top of that hook, it's the height of my nose. So where's the equilibrium position when it's oscillating? At the height of my nose. And it shouldn't take a great leap of logic to figure out that it goes just as far below my nose as it goes above my nose. In other words, the equilibrium position will be in the middle. When I have a pendulum, this is the equilibrium position right here. If I start swinging it, it shouldn't be a big surprise that the pendulum goes just as far on one side of the equilibrium position as it does on the other side. So the equilibrium position is the location with no oscillation. If you don't like the word oscillation, you can use vibration, you can use motion. The nice thing about frequency and period is frequency and period mean the exact same thing they do here as they did with circular motion. With a slight variation. You know, the frequency of circular motion was how many times it went in a circle per second. The frequency of a simple harmonic oscillator is how many times it goes through a complete cycle in a second. So it's the number of complete oscillations in 1 second. And it's measured in hertz. So I don't know if I can get a very high period here. I'm going to give it a shot. I'm going to take a very tiny spring, this little guy. I don't even know how I'm going to rig this up. There we go. That's pretty high frequency. I mean, I don't know that it's 5 times per second, but I don't know if I'll be able to measure that. I'm going to go for 10. Let's see. That's about 2 hertz. Don't worry about what I didn't measure the frequency, I measured the period and then I calculated the frequency. It's taken about half a second to do that once, 0.49 seconds. So that means it's going twice per second. But that brings up the relationship between period and frequency, which we should already know. Period is the time. By the way, this is called F, this is called T. Period is the time for one complete oscillation. And that's measured in seconds. And the relationship between these two, of course, is that period is 1 over frequency. If frequency is how many times per second, and period is how many seconds per time, they are reciprocals of each other. Hypnotizing. Displacement. Displacement refers to, let me explain it first. Displacement refers to where the mass, whether it's the pendular mass or the spring mass, where it is compared to the equilibrium position. So this is a displacement from the equilibrium position. And that's really the definition. You know what displacement is. Displacement is how far and in what direction. So remember when I said that the equilibrium position, if we use the top of the hook of this system is my nose, then if this is in oscillation, anytime this mass is below my nose, it has a negative displacement. Anytime it's above, it has a positive displacement. So the displacement, I'm going to freeze time, the displacement right here might be negative 5 centimeters. And then when it gets to here, it might be negative 6. And then at the very bottom, it might be negative 12 centimeters. The amplitude is the maximum displacement. So if I told you that I pulled it down so that the displacement was negative 12 centimeters, I pulled this mass down, I let it go, then the amplitude will be negative 12, the amplitude rather will be 12 centimeters. We don't use the negative. It just means that it's going to go 12 centimeters below and 12 centimeters above. It's the maximum displacement. Restoring force is the force. This is going to be the most important aspect in the coming days. The force that acts to bring the mass to the equilibrium position. Again, when you talk about a vertical spring, this is complicated to analyze in terms of forces, because at some points in time, the restoring force here is a combination of gravity and the spring force. Right? Like at this point in time right here, remember the equilibrium position is my nose. The restoring force is the force that pulls this back to the equilibrium position, which would be the force that the spring exerts on it. But when it's up here, it's mainly the force of gravity that's causing the restoration of the position. However, at the bottom, yes, the spring is pulling it up, but it's fighting against gravity. So gravity plays a role there as well. It's complicated. When we look at a pendulum, The restoring force is basically the force of gravity, except, and we'll deal with this when we get to pendulums, except the force of gravity is acting down here, and that's not going to restore it. You're looking at the force of gravity that is in that direction, perpendicular to the string. That's the component of gravity that is acting at that instant to get the mass back to where it belongs. Two examples. So this is a very basic introduction. Two quick examples, which you could probably do on your own. What is the frequency of an automobile engine in which the pistons oscillate with a period of 0.0625 seconds? Well, what you are told here is the period, as we've learned today, this frequency formula, or help a guy out here. Is this on your formula sheet this way? Probably. Yeah. So as we learned today, this formula, period equals 1 over frequency, is a more generalized statement. We're going to be able to use it for waves. We're going to be able to use it for simple harmonic oscillators like masses on springs and pendula. We can use it for bumblebee wing flaps. We can use it for circular motion, or we can use it for pistons. The frequency is going to be the reciprocal of that. Alex, help me out here.
16.
Exactly. Okay. So that means that the pistons are firing 16 times per second. So the piston goes from this location, it goes through its cycle and goes back up 16 times. There's a part of the piston that's the arm that changes direction. So the piston moves back and forth, but there's something else driving a gear that is going to spin, and that's why we say that's the frequency of the engine. How many oscillations does the piston make in 3 minutes? Well, we can just use a ratio here. This is 16 oscillations per second, so 3 minutes is 180 seconds. Is that right? Get your thinking caps on. I think so. 60 times, okay. So it's just a ratio here. You don't need a formula for this. It's 16 oscillations or piston rotations per 1 second, x over 180. This is an O, not a 0. Seconds. We're just going to go 16 times 180. So about 2,880. Oscillations. Any questions with number 1? All right, number 2. An electronic buzzer of some kind is making a total of 240,000 buzzes or oscillations in 1 minute. What's the frequency in the period? Well, frequency is the number of oscillations per second. I mean, you're not really using a formula here to answer this first part. You're using the definition of frequency. And this is making 240,000 oscillations, buzzes, back and forths in 1 minute, which is 60 seconds. So it's just a matter now of dividing those numbers. $4,000. And we would write that not as oscillations per second. You would probably just write hertz. If you want to find the period, well, you just take the reciprocal of the frequency. I want to say 0.0025. Or is it an extra 0?
2.5 times 10 to the negative 4.
So negative 4, okay? Which is 0.00025. And that's it. I hope that this little mini lesson gave you some background in terms of some of the things we're going to be doing in the unit, in terms of period and frequency. Not just the formulas, but in terms of what we're actually talking about. We're talking about these things hanging from the ceiling. I'm going to hand back your exams. You have about a half hour here left in class, so you have some textbook problems that I would like you to complete for tomorrow.